A supernova is a rare astronomical event that occurs during the last stellar evolutionary stages of a massive star's life, whose dramatic and catastrophic destruction is marked by one final titanic explosion. For a short time, this causes the sudden appearance of a new, bright star in the heavens, before slowly fading from sight over several weeks or months. Only 3 Milky Way naked-eye supernova events have been observed during the last 1,000 years, though many have been telescopically seen in other galaxies. The most recent directly observed supernova in the Milky Way was Kepler's star of 1604, but remnants of 2 more recent supernovae have been found retrospectively. Statistical observations of supernova in extragalactic galaxies suggest they should occur on average about 3 times every century in the Milky Way, and that in any galactic supernova would almost certainly be observable in modern astronomical equipment. Supernovae are more energetic than novae. In Latin, nova means new, referring astronomically to what appears to be a temporary new bright star. Adding the prefix super distinguishes supernovae from ordinary novae, which are far less luminous. The word supernova was coined by Walter Bader and Fritz Zwicky in 1931. It is pronounced supernovae, with the plural supernovae, supernovae, or supernovas, during maximum brightness. The total equivalent radiant energies produced by supernovae may briefly outshine an entire output of a typical galaxy and emit in energies equal to that created over the lifetime of any solar-like star. Such extreme catastrophes may also expel much, if not all, of its stellar material away from the star, at velocities up to 30,000 kilometers per second, or 10% of the speed of light. This drives an expanding and fast-moving shock wave into the surrounding interstellar medium, and in turn, sweeping up an expanding shell of gas and dust, which is observed as a supernova remnant. Supernovae create, fuse and eject the bulk of the chemical elements produced by nucleosynthesis. Supernovae play a significant role in enriching the interstellar medium with higher mass elements. Furthermore, the expanding shock waves from supernova explosions can trigger the formation of new stars. A great proportion of primary cosmic rays comes from supernovae, and they are also potentially strong galactic sources of gravitational waves. Theoretical studies of many supernovae show they can be triggered by one of 2 basic mechanisms. This can be by sudden reignition of nuclear fusion in a degenerate star, or by the sudden gravitational collapse of the massive star's core. In the first instance, a degenerate white dwarf may accumulate sufficient material from a binary companion, either through accretion or via a merger, to raise its core temperature to then trigger runaway nuclear fusion, completely disrupting the star. In the second case, the core of a massive star may undergo sudden gravitational collapse, releasing gravitational potential energy that can create a supernova explosion. Observations do show there are more uniqueness or complexities to these 2 simple alternatives mechanisms, but the astrophysical collapse mechanics have been accepted and established by most astronomers for some time. Due to the significant number of diverse astrophysical consequences of these supernovae events, astronomers now deem supernovae studies across both stellar and galactic evolution as most important among their many lines of study. Observation history. The earliest recorded supernova, SN 185, was viewed by Chinese astronomers in 185 AD, with the brightest recorded supernova being SN 1006, which was described in detail by Chinese and Islamic astronomers. The widely observed supernova SN 1054 produced the Crab Nebula. Supernovae SN 1572 and SN 1604, the latest to be observed with the naked eye in the Milky Way galaxy, had notable effects on the development of astronomy in Europe because they were used to argue against the Aristotelian idea that the universe beyond the Moon and planets was immutable. Johannes Kepler began observing SN 1604 at its peak on October 17, 1604, and continued to make estimates of its brightness until it faded from naked view a year later. It was the second supernova to be observed in a generation. Before the development of the telescope, there have only been 5 supernovae seen in the last millennium. In the perspective of how long a star's lifetime is, its death is very brief. In fact, a star's death may only last a few months. Due to this, a typical human will only experience this rarity, on average, once in their lifetime. This is a microscopic fraction in comparison to the 100 billion stars that compose a galaxy. Since the development of the telescope, the field of supernova discovery has extended to other galaxies. Starting with the 1885 observation of supernova S Andromeda in the Andromeda Galaxy, American astronomers Rudolf Minkowski and Fritz Zwicky developed the modern supernova classification scheme beginning in 1941. In the 1960s, astronomers found that the maximum intensities of supernova explosions could be used as standard candles, hence indicators of astronomical distances. Some of the most distant supernovae recently observed appeared dimmer than expected. This supports the view that the expansion of the universe is accelerating. Techniques were developed for reconstructing supernova explosions that have no written records of being observed. The date of the Cassiopeia A supernova event was determined from light echoes off nebulae, while the age of supernova remnant RxJ0852 was estimated from temperature measurements and the gamma-ray emissions from the decay of titanium-44. In 2009, nitrates were discovered in Antarctic ice deposits that matched the times of past supernova events. The brightest observed supernova ASASSN 15LH was detected in June 2015, twice as luminous as the previous record holder. At peak brightness, ASASSN 15LH was as bright as 570 billion suns. Discovery. Early work on what was originally believed to be simply a new category of novae was performed during the 1930s by Walter Baade and Fritz Zwicky at Mount Wilson Observatory. The name supernovae was first used during 1931 lectures held at Caltech by Baade and Zwicky, then used publicly in 1933 at a meeting of the American Physical Society. By 1938, the hyphen had been lost and the modern name was in use. Because supernovae are relatively rare events within a galaxy, occurring about 3 times a century in the Milky Way, obtaining a good sample of supernovae to study requires regular monitoring of many galaxies. Supernovae in other galaxies cannot be predicted with any meaningful accuracy. Normally, when they are discovered, they are already in progress. Most scientific interest in supernovae, as standard candles for measuring distance, for example, require an observation of their peak luminosity. It is therefore important to discover them well before they reach their maximum. Amateur astronomers, who greatly outnumber professional astronomers, have played an important role in finding supernovae, typically by looking at some of the closer galaxies through an optical telescope and comparing them to earlier photographs. Toward the end of the 20th century, astronomers increasingly turned to computer-controlled telescopes and CCDs for hunting supernovae. While such systems are popular with amateurs, there are also professional installations such as the Katzmann Automatic Imaging Telescope. Recently, the Supernova Early Warning System project has begun using a network of neutrino detectors to give early warning of a supernova in the Milky Way galaxy. Neutrinos are particles that are produced in great quantities by a supernova explosion, and they are not significantly absorbed by the interstellar gas and dust of the galactic disk. Supernova searches fall into 2 classes: those focused on relatively nearby events and those looking for explosions farther away. Because of the expansion of the universe, The distance to a remote object with a known emission spectrum can be estimated by measuring its Doppler shift. On average, more distant objects recede with greater velocity than those nearby, and so have a higher redshift. Thus the search is split between high redshift and low redshift, with the boundary falling around a redshift range of Z equals 0.1 minus 0.3, where Z is a dimensionless measure of the spectrum's frequency shift. High redshift searches for supernovae usually involve the observation of supernova light curves. These are useful for standard or calibrated candles to generate Hubble diagrams and make cosmological predictions. Supernova spectroscopy, used to study the physics and environments of supernovae, is more practical at low than at high redshift. Low redshift observations also anchor the low distance end of the Hubble curve, which is a plot of distance versus redshift for visible galaxies. Naming convention. Supernova discoveries are reported to the International Astronomical Union's Central Bureau for Astronomical Telegrams, which sends out a circular with the name it assigns to that supernova. The name is the marker SN followed by the year of discovery, suffixed with a 1 or 2-letter designation. The first 26 supernovae of the year are designated with a capital letter from A to Z. Afterward, pairs of lowercase letters are used. A, AB, and so on. Hence, for example, SN2003C designates the third supernova reported in the year 2003. The last supernova of 2005 was SN2005-NC, indicating that it was the 367th supernova found in 2005. Since 2000, professional and amateur astronomers have been finding several hundreds of supernovae each year. Historical supernovae are known simply by the year they occurred. SN 185, SN 1006, SN 1054, SN 1572 and SN 1604. Since 1885 the additional letter notation has been used. Even if there was only one supernova discovered that year, this last happened with SN 1947A. SN, for supernova, is a standard prefix. Until 1987, two-letter designations were rarely needed. Since 1988, however, they have been needed every year. Classification. As a part of the attempt to understand supernovae, astronomers have classified them according to their light curves and the absorption lines of different chemical elements that appear in their spectra. The first element for division is the presence or absence of a line caused by hydrogen. If a supernova's spectrum contains lines of hydrogen, it is classified type 2, otherwise it is type 1. In each of these two types there are subdivisions according to the presence of lines from other elements or the shape of the light curve. Type 1. The type 1 supernovae are subdivided on the basis of their spectra, with type Iowa showing a strong ionized silicon absorption line. Type 1 supernovae without this strong line are classified as type Sib and IC, with type Ib showing strong neutral helium lines and type IC lacking them. The light curves are all similar, although type Iowa are generally brighter at peak luminosity. But the light curve is not important for classification of type 1 supernovae. A small number of type Iowa supernovae exhibit unusual features such as non-standard luminosity or broadened light curves, and these are typically classified by referring to the earliest example showing similar features. For example, the subluminous SN 2008 hectares is often referred to as SN 2002CX-like or class IA2002CX. Type 2. The supernovae of Type 2 can also be subdivided based on their spectra. While most Type 2 supernovae show very broad emission lines which indicate expansion velocities of many thousands of kilometers per second, some, such as SN 2005 GL, have relatively narrow features in their spectra. These are called type IIN, where the N stands for narrow. A few supernovae, such as SN 1987K and SN 1993J, appear to change types. They show lines of hydrogen at early times, but, over a period of weeks to months, become dominated by lines of helium. The term type IIb is used to describe the combination of features normally associated with types II and Ib. Type II supernovae with normal spectra dominated by broad hydrogen lines that remain for the life of the decline are classified on the basis of their light curves. The most common type shows a distinctive plateau in the light curve shortly after peak brightness, where the visual luminosity stays relatively constant for several months before the decline resumes. These are called type IIp, referring to the plateau. Less common are type IIL supernovae that lack a distinct plateau. The L signifies linear, although the light curve is not actually a straight line. Supernovae that do not fit into the normal classifications are designated peculiar, or PEC. Types III, IV, and V. Fritz's wiki defined additional supernovae types. Although based on a very few examples that didn't cleanly fit the parameters for a Type I or Type II supernova, SN 1961I and NGC 4303 was the prototype and only member of the Type III supernova class, noted for its broad light curve maximum, and broad hydrogen Balmer lines that were slow to develop in the spectrum. SN 1961F in NGC 3003 was the prototype and only member of the Type IV class, with a light curve similar to a Type IIp supernova, with hydrogen absorption lines but weak hydrogen emission lines. The Type V class was coined for SN 1961b and NGC 1058, an unusual faint supernova or supernova imposter with a slow rise to brightness, a maximum lasting many months, and an unusual emission spectrum. The similarity of SN 1961b to the Eta Carini Great Outburst was noted. Supernovae in M101 and M83 were also suggested as possible Type IV or Type V supernovae. These types would now all be treated as peculiar Type II supernovae, of which many more examples have been discovered, although it is still debated whether SN 1961b was a true supernova following an LBB outburst or an imposter.